As Tim mentioned, my name is Arun Konanur. I'm based in London, Ontario, Canada. For the past 5 years and change, I've been doing research in what I call genealogical bioinformatics. This is my second talk for the GFI. I spoke to you folks previously in October of 2024. I'm really glad to be back with new ideas. To date, I've filed 5 patents for processes which analyze associations in autosomal DNA. My feeling is that the genealogical bioinformatics is genetic genealogy's next big thing. How we'll take everything we know about genetic genealogy and marry it up with information science, a little bit of math. These methods are very AI friendly. So it's my feeling that as the field of AI grows, our ability to analyze these matches is going to continue as well to grow. Welcome to further adventures in genealogical bioinformatics. What's new? What's next? I would like to thank Tim and Lisa and the GFO and the Portland chapter of ISOG for inviting me to speak to you all for the second time, as this presentation is something of a sequel to my previous talk from October of 2024. As Tim introduced, I'm Arun Konanur, and as you can see from the attractive logo on screen, my little corner of the internet is discoveringnewancestors.com. Please feel free to visit whenever the mood strikes. I have information about the topics I'll be covering in today's presentation, along with downloadable resources, case studies, and other informative materials. As I mentioned, this presentation is something of a continuation of my previous talk given to the GFO in October 2024. I'll touch on a few highlights from that lecture. Everyone should be able to follow along, I hope, but I'd certainly recommend having a look at my previous presentation if you get the chance to do so. It's on the GFO YouTube channel. Here's a link to the talk if that's at all helpful. Today's presentation became necessary for several reasons, one being that my previous talk had already run to well over an hour and contained all kinds of detailed information which tied itself up nicely as far as it went. But afterwards, I realized that I needed to revisit the topic of shared DNA matches, in that shared DNA matches remain an incredibly powerful tool for exploring our DNA results. And in the months since I last spoke to you all, I've discovered new ways to employ shared DNA matches, which we'll discuss today. Now, before we get to all the good stuff, a word from my legal department. The bioinformatic processes I'll discuss today in this presentation are patent-pending processes of Discovering New Ancestors, Inc. By this, I'm referring to any of the processes accessible through my bioinformatics page at discoveringnewancestors.com. There are 5 processes to date. All rights are reserved. This presentation remains the intellectual property of Discovering New Ancestors. However, permission is granted for non-commercial use of these processes via the desktop prototypes I have available through my website at discoveringnewancestors.com. Commercial and database management system implementations of these processes require prior written approval from Discovering New Ancestors, Inc. And what that means is that you're welcome to use my prototypes and materials for your own research, but if you're going to attempt anything commercially with them, I'd like to hear about it. And again, you can find more information concerning everything I get up to genealogically at discoveringnewancestors.com. Let's review a few highlights from my previous talk, just to get everyone up to speed. So genealogical bioinformatics, what is it? Well, the explanation I offer anyone who cares to listen is that genealogical bioinformatics is how future challenges in genetic genealogy will be solved through AI. And by that, I mean that genealogical bioinformatics offers a way of modeling long-standing problems in genetic genealogy in a manner that computer systems and AI can understand, mostly through pattern recognition. And what is bioinformatics? Well, it's an interdisciplinary field of science that develops methods and software tools for understanding biological data, especially when the data sets are large and complex. For genealogists, the human genome is our biological data, with around 3.2 billion base pairs, and the genome, along with our DNA matches, which may consist of upwards of 50, 60, 100,000 matches for an individual, form a large and complex data set. And so when we speak of genealogical bioinformatics, we're talking about a hybrid discipline that uses biology, information engineering, and mathematics to address problems in the field of genetic genealogy. Something I mentioned in my previous talk is that insofar as biology is concerned, any experienced genetic genealogist already knows more about the subject than I'm going to refer to in today's lecture. The information engineering aspect of today's processes primarily involve looking at familiar concepts in genetic genealogy in new and interesting ways. And as for the math, much of that work actually happened when I was developing the shared match tool that I'll be discussing today. And so that work, which was primarily logic and set theory based, is actually covered off in my previous presentation. So you don't need to be thinking about math very much in any of this. So in case this slide makes you nervous, don't be. This presentation is about genealogy. more or less. Now, a word of caution, one of the selling points of genealogical bioinformatics, at least as I see it, is that this field is able to address long-standing problems in genetic genealogy in a manner that is AI-friendly, which is to say that the tools and methods employed by genealogical bioinformatics can easily be replicated and deployed by computer systems, so that their greatest usefulness doesn't lie with individual researchers crunching data at their desk, but rather when these tools are built into the reporting systems of DNA testing providers who already warehouse and interpret massive amounts of data. This means that the things which make the methods I'll discuss today useful and AI-friendly are the same things that make them cumbersome for consumers. Things like downloading a full set of DNA matches for yourself and doing the same for each of your matches can take time, and it's something that's unusual for a lot of people. Nevertheless, exploring these processes provides valuable insights into the underpinnings of shared matches and the substance of our DNA test results. We'll begin by reviewing one of the issues discussed in my previous presentation, an issue concerning the utility of shared matches, which is fundamental to the methods we'll review today. Now, when we speak of the utility of shared matches, we refer to the idea that three individuals who share DNA with each other will, at least in theory, share a common ancestral couple. This is very often the case, especially when individuals share a reasonable amount of DNA, say greater than 100 centimorgans. In my previous presentation, I referred to this as a favorable trio because the structure of this shared match trio supports building quick trees in order to research the pedigree of each of the matching individuals to discover their common ancestral origins, which is a favorable outcome for certain. However, despite the prevalence of favorable trios, another possibility exists, especially as the amount of DNA shared among the members of the trio decreases. We'll begin with two individuals who share DNA, and if this shared DNA is from a valid identical by descent match, then it's not unreasonable to conclude that these people share a common ancestral couple somewhere in their respective pedigrees. To this shared match, we'll add another individual who shares DNA with one half of our shared match, but does so along a distinct ancestral line, as I've illustrated here. From here, we can imagine a situation where our third individual also shares DNA with the other half of our original shared match, perhaps through a distant or as yet undiscovered ancestral connection. In this instance, we also have a shared match trio, three individuals who match each other, but no amount of research will lead you to an ancestral couple from whom all three individuals descend. In fact, the more you research the pedigrees of these individuals, the farther you get from a neat solution offered by the favorable trio. And for this reason, we call this an unfavorable shared match trio. Now, the real problem with favorable and unfavorable shared match trios, especially as they relate to your personal research and how your DNA testing provider reports on them, has to do with basically how do we tell them apart? And ideally, how do we do this in a way that can be done in real time, so our DNA test results will reflect this. In my previous presentation, I explored a number of strategies for differentiating shared match trios, and ultimately arrived at a method which uses the full sets of DNA matches of each member of the trio to generate a value, shown here as V. And the idea of this formula is that if we take the number of DNA matches shared by all three of our individuals and divide that by the largest number of matches shared by any two of the individuals in our trio, after limiting the centimorgan range of matches that we examine to a lower threshold of 40 centimorgans and upper threshold of 400 centimorgans, we derive this value. And the development of this formula is discussed in great deal in my previous GFO talk, so I'm not going to go into how I built the formula here, but the basic idea is that an unfavorable trio will produce a value near zero, and a favorable trio will produce a larger value ranging from 8% upwards. I call this process shared match differentiation, or SMD, and beyond identifying types of shared match trios, the process can do a few other things, which I explored in some detail in my previous talk. The shared match trio can evaluate larger groups of DNA matches, more than 3 people, 4, 5, and 6, and so on. It can validate existing family trees using DNA test results. The process can be used to generate rough prospective trees indicating which tested individuals might be related along specific ancestral lines. The process can proofread collections of DNA matches created or employed by other bioinformatic processes, and we'll return to this last point as we explore new uses for shared match differentiation. To carry over one final point from my previous presentation, researchers can perform shared match differentiation on a desktop computer by using my SMD utility after downloading the full sets of DNA matches from 3 kits which they administer. I use the DNA GEDCOM utility for this purpose, and then you paste the member names, kit IDs, and shared centimorgan values into the SMD Utilities Microsoft Excel interface, and full details and a user guide are available on my website at the link provided on the screen here. So, with our quick review out of the way, what's new and what's next in genealogical bioinformatics? Well, today I'd like to present 2 extensions of the SMD process, which didn't fully occur to me at the time of my previous presentation, and which, even if they did, would have made my previous talk unwieldy in length. Our first extension to the shared match differentiation process concerns its ability to proofread cluster matrices. This particular application of SMD occurred to me right around the time our friends at Ancestry rolled out their clustering tool. Here's a sample output of Ancestry's DNA Pro Tools clustering output, which I grabbed from one of Dana Leeds' YouTube videos. You can follow the link at the lower right to view the example in its original context. In Dana's presentation, she mentions that the gray square, which I've highlighted inside the red circle, is an example of an outlier match. In this case, it is a situation where 2 individuals aren't from the same ancestral family, happen to match each other along a third, otherwise undefined connection. Of course, this sounds a lot like what happens in the context of an unfavorable shared match trio. And at this point, it occurred to me that every shaded square in this diagram is an example of a shared match trio, a trio consisting of the DNA test taker. In this example, we're clustering Dana's own matches, and the individuals on the horizontal and vertical axes of the chart. If we were to download the entire set of Dana's DNA matches and the full set of DNA matches for the 2 individuals indicated by the arrows, and use these as inputs for the SMD tool, the tool would report that this was an unfavorable trio, and so we could either flag or suppress the gray square in this location. Because the SMD process isn't concerned with the ordering of individuals in our trio, the findings of our test also apply to the same combination of individuals on the other side of the central diagonal axis, as indicated by the curved arrow there. And here's what the cluster would look like with these 2 outliers suppressed. Now, if we had access to the full set of DNA matches for every individual listed in the matrix, we could proofread the entirety of the diagram, flagging or suppressing unfavorable trios wherever they might occur. As before, we only need to test half of the diagram in order to evaluate the entire cluster matrix. We could even test squares which aren't shaded. The SMD utility would designate those unshaded squares as non-trios when they are used as inputs into the SMD utility. Of course, because no one would have access to the full set of DNA matches for every individual in this diagram, this use of the SMD process would be best implemented if the protocol were built into the server-side reporting of a DNA testing provider, where it could be used to output quality clusters free of spurious outlier matches, which hopefully maybe will happen someday. What else is new? Well, there's something else which I call endogamic tailoring, and it's a method for normalizing endogamous populations. But before we dig into the specifics of the process, we need to properly cover off the topic of, you guessed it, endogamy. So let's begin. What is endogamy? Well, by definition, it's the practice of marrying within the same ethnic, cultural, social, religious, or tribal group. From the standpoint of genetics, this means that we're looking at a restricted or limited gene pool. People in such a group will be related to each other along multiple ancestral pathways, and what this means is that your matches will share more DNA with each other than they should, given their genealogical distance. It means that many DNA matches may have no discernible common ancestor. And lastly, your test results will show numerous DNA matches. And by that, I mean that if the test results of an average individual might consist of DNA matches of 10 or 20,000 or maybe 40,000 matches, an individual with endogamy in their lines could have anywhere from 70 to 100,000, even 200,000 DNA matches in their roster. Even with all of that, you may ask yourself, well, what's the problem? And the problem is that many of our tools for investigating DNA matches, tools like the Shared Centimorgan project, which I've shown here, or DNA Painter's What Are the Odds tool, and other tools, depend on DNA matches which fall into an accepted range of shared linkage based on the number of meiotic divisions implied by a given relationship. So when we see a 1600 centimorgan match, we think uncle or half-sibling rather than first cousin or great-grandchild. Endogamy has the effect of upending these norms, especially since its effects vary from case to case. A misconception concerning endogamy is that it's an either-or proposition, that you either come from an endogamous population or you don't. So that folks with French-Canadian ancestry or Akkadian, Cajun, Mennonite, or Ashkenazi Jewish ancestry need to be concerned about this, but the rest of us can ignore the concept. In fact, endogamy is more like the illustration on the right. Everyone has some degree of endogamy in their DNA results, especially as we investigate smaller matches. So while it's true that people from the aforementioned ethnic groups need to be especially mindful of endogamy in and amongst their ancestral lines, to a greater or lesser extent, we all need to be aware of endogamy's implications. I like to remind myself as we move back in time, our direct ancestors increase in number at the same time that the world's historical population gets smaller. So it's inevitable that eventually everyone's pedigree collapses to some extent. I may be dating myself somewhat here, but I find a useful visualization of endogamy in David Byrne's Big Suit from the Talking Heads 1984 concert film Stop Making Sense. As such, endogamy gives you this when you want this. And the idea of a clothier altering or taking in the suit on the left so that it looks more like the suit on the right is what gave me the idea to call my process of mitigating the effects of endogamy endogamic tailoring, which we'll discuss shortly. Before we do, however, there are a few other things I need to cover off, and one of those is the distinction between endogamy and pedigree collapse. It's an important distinction, especially when we consider that we want to mitigate the effects of endogamy. Endogamy is something we can mitigate. Pedigree collapse is not. The distinction is essentially between a pervasive, systemic, historical practice versus specific occurrences which can be charted in your family tree. The former we can compensate for in a variety of ways. The other we can't. Now I'll give you a specific example from my own family to illustrate what I'm talking about. My father is from southern India, and in his culture, arranged marriages are common and have been for centuries. And these marriages are typically arranged between people within a given social class called a caste. And my father's DNA matches, and by extension my own matches with people from the Indian subcontinent, display all the signs of endogamy I discussed previously. Dad's DNA matches share more DNA than they should. What looks like a second cousin may actually be a fourth cousin or even more distant relation. And many of his matches have no discernible common ancestor. The only thing that prevents him from having thousands and thousands of DNA matches is the fact that relatively few people of Indian extraction have tested their DNA. So my father already has endogamy amongst his DNA matches, and the idea of mitigating endogamy is to bring his DNA results more in line with what we would expect to see. However, there are things in my father's ancestry which go beyond endogamy, and these things can't be mitigated, at least not without materially distorting his DNA results. Here's an example. As the result of an arranged marriage, my aunt, my father's sister, is married to her first cousin. That's not endogamy, it's pedigree collapse, and no amount of segmental magic is going to change the fact that my father and I will share more DNA than we should with my cousin at the left end of this diagram. That's to be expected because, as you can see on the right end, there are fewer sets of great-grandparents than there should be. And there's no getting around that. It's not something that's going to change with any kind of segmental downweighting because we can't untangle these ancestral lines. However, there are strategies for doing what can be done. Perhaps the best known and certainly the most widely encountered protocol to mitigate the effects of endogamy is Ancestry DNA's Timber. Timber is an algorithm which downweights, which is to say it discards or suppresses small DNA segments. This is done based on the likelihood that these common segments come from genetic pileups and are shared with many individuals from the same ancestral region. These pileups raise the distinction between IBS, or identical by state, also known as identical by chance segments of DNA, and IBD, or identical by descent segment. IBS segments exist among individuals who originate from the same geographic region, be it India or Ireland or Appalachia. IBD segments, identical by descent segments, are inherited from our direct ancestors and are what allows genetic genealogy to function at all, really. In order to identify IBS segments, Timber takes what we call a population genetics approach by surveying which segments most likely originate from ancient ancestral connections. I can't speak to the specifics of this process because it's proprietary, but there are a few resources available which I've linked to in the syllabus. What I can tell you is that Timber downweights or excludes small segments of 50 centimorgans and less on matches which themselves are at most 90 centimorgans inside. Because different ancestral populations will have unique pileup regions, timber effectively employs a one-size-fits-many, but not all approach. For instance, timber doesn't appear to do much in the way of anything for my father's DNA matches, since the gene pool of southern India is fairly far removed from where the majority of Ancestry DNA's testers originate, which is closer to northern Europe. Now, what does this mean from a practical standpoint? Let's say we have two individuals, A and B. Well, our standard matching process can be thought of as taking subject A's DNA, as measured by a testing company's methods, and evaluating the portion of those test results which are shared by subject B, as expressed in centimorgans. And that pretty much is what happens when we evaluate close family matches. So if my son takes a DNA test or my first cousin takes a DNA test, this is going to be what's reported. My DNA and how much is shared with subject B's DNA, and we report it as X centimorgans of DNA. Where timber is concerned, or as discussed in the case of any population genetics-based model, we would evaluate our subjects' shared DNA normally, and then downweight pileup segments of DNA as timber sees them. In the case of timber, this occurs if our subject's shared DNA is less than 90 centimorgans. You'll notice that timber's pileups of DNA are noted as EP timber. I use the EP notation to denote that the DNA segments downweighted by timber don't reflect the results of a single DNA test, but rather are a fabricated set of segments, which I refer to as an endogamic profile. Now let's consider another way of managing endogamy among DNA test subjects, what I've called endogamic tailoring. If we were to construct endogamic profiles for every individual in our testing provider's roster, and then those endogamic profiles could be tailored to reflect pileups resulting from a specific subject's genetic inheritance and pedigree. That's the thinking behind endogamic tailoring that I've developed here. As you can see, we have EPA, which is the endogamic profile for individual A's DNA. We have EPB, the endogamic profile for subject B's DNA, and the little bracket there in between EP and DNA indicates that we're in negation, that we take subject A's DNA, we negate their endogamic profile by suppressing those segments, and then we do the same for subject B in negating their endogamic profile, and then we see what's left over, how much is shared between the two of them, and that's reported in X centimorgans. So how do we create these custom endogamic profiles? Well, the process of endogamic tailoring employs shared match differentiation, tool available on my website, to generate endogamic profiles. Now, I should mention that soon after filing the patent application for my SMD process, I had a strong sense that the processes had applications beyond telling differentiating shared match trios apart, but I couldn't quite articulate what precisely. Over time, endogamy seemed like a logical application for the SMD process, but I still couldn't quite wrap my mind around it because endogamy at the time seemed so big that I couldn't quite see my way clear to fitting the ideas together. I'll begin where the idea for endogamic tailoring began, which was an example from my previous GFO talk. In my previous talk, I spoke about how the SMD process can proofread collections of DNA matches created or employed by other bioinformatic processes, and the example I used in my previous talk was that back in 2021, I filed my first patent application for a bioinformatic process that I call CMA, which stands for Correlated Multiphasic Analysis. And while the specifics of that process could easily require a separate presentation, the basic idea is that everyone has a brick wall ancestor, someone for whom, try as you might, you can't find documentary evidence, someone who doesn't turn up in anyone else's family tree, and for whom you don't have any obvious DNA connections beyond your immediate family. In short, an ancestor whose pedigree is essentially one big question mark. CMA uses your DNA matches and your documented connection to your brick wall ancestor and the DNA matches of other family members who are known to descend from your brick wall ancestor, even if they're distant cousins or half relations, and CMA correlates the in common with matches of those cousins and their generation of connection to assemble a genetic complex, a collection of individuals connected to you through the pedigree of your brick wall ancestor. Now, CMA's genetic complex is a list of individuals who share DNA exclusively with various combinations of the descendants of your brick wall ancestor. And you can see a sample of this list on screen. It's a collection of individuals who match our test subjects A and B in the range of 15 to 41 centimorgans. We'll make note of one entry in our list of shared matches. This individual, we'll call him SP, shares 39 centimorgans of DNA with my cousin DS, who is letter A, and he shares 34 centimorgans of DNA with my other cousin CG, indicated by the letter B. Now, these these aren't huge matches, but I was encouraged to investigate this connection to my family because of its possible connection to my brick wall ancestor, and also because, like myself, SP appears to have a well-researched and documented online tree. Of course, I looked and looked and looked, and I couldn't see any sort of plausible connection between SP's family lines and my own, or anything suggesting a connection to my brick wall ancestor. So I made note of this impasse and I moved on. Now, in addition to his family tree, SP granted me shared access to his DNA matches. And so when I developed the SMD process, I went back to the shared match trio formed by my cousins and SP, and I discovered that they form an unfavorable trio. So it wasn't surprising that I couldn't find a connection between our family trees, as a single ancestral connection simply doesn't exist. Now, the implication of an unfavorable trio among my cousins DS and CG and their mystery match SP is that since we know that my cousins share common grandparents, SP would likely match one cousin DS through the ancestral line he doesn't share with CG, and SP would match CG through the ancestral line that she doesn't share with her cousin DS. And that's fine as far as it goes until we consider that the grandparents DS and CG share originate from the United Kingdom, and DS maternal line comes from Eastern Europe, from what is now Ukraine, and CG's maternal line originates in Central Europe, in Germany. The problem arises, however, when we consider that SP's ethnicity breakdown is exclusively from the United Kingdom and Scandinavia, and doesn't include ancestors from either of these other regions. How does that work, knowing that we have an unfavorable trio? Well, the solution is that SP must be connected to DS and CG through their common British heritage. But then, why is this an unfavorable trio? The answer begins with what we know, that DS and CG do share a set of common grandparents, just as we would expect any first cousins to do. These grandparents are of British ancestry, which is to say their parents and grandparents and great-grandparents and so on, well, were all born in the United Kingdom. From this standpoint, it's not difficult to imagine that the 39 centimorgans of DNA SP shares with DS and the 34 centimorgans SP shares with CG doesn't originate from a single ancestral connection, but rather from multiple ancestral lines, each sharing a small amount of DNA with DS and CG. And so we've stumbled upon a different type of unfavorable shared match trio, a trio where people are related to each other on multiple ancestral pathways, where matches share more DNA than they should. In this case, SP shares 39 centimorgans with my cousin DS and 34 centimorgans with my cousin CG. And we see that our DNA matches have no discernible common ancestor. Of course, if these bullet points sound familiar, it's because they're all properties of our old friend Endogamy. And so we find that we have identified three types of shared match trio. One favorable type, where our three matches share a common ancestral couple, and two types of unfavorable trio. We'll refer to the type of shared match trio with multiple distant ancestral connections as an endogamous shared match trio, and we'll contrast this with what I'll call an exogamous shared match trio. Now, this is a significant distinction, but you may wonder, how does this bring us any closer to a strategy for mitigating endogamy? Well, to get where we're going, we need to reference another concept, one which will be largely familiar to most of you, and that's the concept of triangulation. Now, you'll find various interpretations of this term, but the rigorous definition is that triangulation requires 3 or more test subjects. Additionally, all our subjects must match, which is to say they mutually share DNA. Further, in addition to sharing DNA, our subjects must share identical segments of DNA on one or more chromosomes at the same position. Not every favorable shared match trio will triangulate, which is why we don't use triangulation to perform shared match differentiation. However, the triangulated segments of a favorable shared match trio provide genetic evidence of a common ancestral couple, and that's an important finding. In fact, our bottom line takeaway here will be that the triangulated segments of a favorable shared match trio originate from a common ancestral couple. We can visualize what triangulation looks like. We could use individual A as a reference and map the segments of DNA individual D shares with them. And if individual D is a reasonably close match, they could share several segments of DNA distributed across several chromosomes, as indicated by the dark blue shading. Next, we can plot the DNA shared by individual E with subject A using the light blue color. In the example, individual E is a more distant relation, sharing less DNA with individual A than subject D does. Our triangulated segments are the sections of each chromosome shared by all 3 of our subjects, which I've circled in red. In this case, we're looking at the end of chromosome 6 and a small section near the start of chromosome 8. Although it's useful to have a graphical idea of our shared segments of DNA, what we really want to work with are the dimensions of the triangulated segments themselves. itself. And the site I've used to plot out this shared DNA, in this case I use the compact segment mapper from GEDmatch, it can also output the triangulated data itself. In this case, we have a total of 27.2 centimorgans of DNA originating from the ancestral couple common to all three of these subjects. Now, continuing on, if we were to triangulate the DNA of the members of an exogamous shared match trio, we should find that there's no triangulation. We'll return to this case momentarily, but no triangulation is what we would typically expect from an arrangement such as this. The endogamous shared match trio, however, provides us with unique insights into the broader context of our testing subject's pedigree. If the triangulated segments of a favorable shared match trio present the genetic material of a common ancestral couple, then the triangulated segments of an endogamous shared match trio must represent evidence of not a single common ancestor, but rather evidence of the endogamous segments which give rise to the unfavorable trio itself. As such, we can regard the start and end points of the triangulated segments of an endogamous shared match trio as areas of DNA to be downweighted or otherwise suppressed or made unavailable for matching for each of the individuals in the endogamous shared match trio. We could collect these values in a database, recording both the segments and test kit IDs of the individual members of the endogamous shared match trio. These downweighted segments contribute to the endogamic profile of each of our three test subjects, as all three subjects share the same triangulated segments of endogamous DNA. We repeat this process using any and all unfavorable shared match trios found among the shared matches of our test subject. In this case, we'll continue to work our way through the unfavorable shared match trios of our subject DS, each time recording the start and end points of the triangulated segments of DNA shared by members of each unfavorable shared match trio, along with the kit IDs of the members of the trio. When we fully survey the shared match trios of our test subject, we'll have a curated list of DNA segments which contribute to whatever degree of endogamy is present in our subject's pedigree. This list of segments is our subject's endogamic profile, a collection of DNA segments to be downweighted, which is to say disregarded or otherwise suppressed, when our subject's DNA is matched against the DNA of other test takers. Because each line item in our endogamic profile, a collection of DNA segments to be downweighted, because each line item in our endogamic profile database involves the triangulated DNA of other test takers, our database already contains partial endogamic profiles for other test subjects, as shown here for the subject represented by the tilde character, and for the test subjects represented by the double asterisk. Of course, to properly match the raw DNA of our initial test subject with other test takers, each test subject will require their own endogamic profile, which means surveying the shared match trios of those test subjects as well, which will in turn partially populate the endogamic profiles of other test subjects. But the idea here is that endogamy affects the DNA matches of everyone, so it follows that we'll want to create endogamic profiles for each test taker. You recall that I mentioned that it was unlikely that we would find any triangulated segments among the members of an exogamous shared match trio. Nevertheless, it remains a possibility, especially among highly endogamous populations. Were we to detect even scant evidence of triangulation among these exogamous trios, we'd want to treat those areas as endogamous segments to be excluded as well. Of course, if we find no evidence of triangulation, then nothing changes regarding our map of excluded segments. Finally, in extremely endogamous populations, and my father's subcontinent Indian test results certainly come to mind, testing non-trios, groups consisting of the test subject and any two of their matches, even if the matches don't appear to match each other, could very well yield additional segments to exclude. These would be small segments which fall below the threshold of reporting, but again, I wouldn't consider triangulating segments of non-trios except in the context of extremely endogamous populations, and as before, if no triangulating segments are found, then nothing changes. With each type of unfavorable trio, we're building an endogamic profile for our DNA test taker, and in the process, assembling a partial list of excluded segments for each individual that participates in one or more of our shared match trios. The advantage of compiling this list in a database format is that the list of segments can be reused by querying our master list of endogamous segments with the test kit ID of any test subject. As an aside, since we're excluding portions of the genome from matching, endogamic tailoring makes expressing matches as a percentage of available or unsuppressed DNA more useful than measuring matches in absolute centimorgans, since an endogamous parent-child match will still check in at around 50% of shared DNA, but after downweighting might not equal the same number of centimorgans as it would in a non or less endogamous situation. So, in practice, what really happens to our DNA matches under endogamic tailoring? Well, let's begin with what happens now? Using a rough approximation of the ancestry DNA process as an example. You take a DNA test, your raw data is compared against everyone else's raw data to arrive at a set of DNA matches. Those matches are downweighted by the Timber algorithm, and then you can read those downweighted matches online. That's pretty much what goes on, and it works pretty well. This is the process. This process is how I found that my cousins share 39 and 34 centimorgans of DNA with their mystery match SP. What I'd imagine with the protocol I've described is that instead of, or in addition to, downweighting by a population genetics-based algorithm, we employ the endogamic tailoring process to compile a custom array of segments to be downweighted for each DNA test taker. We would then rerun the matching process and report the results of this second round of matching post-endogamic tailoring. In a situation like this, the unfavorable match my cousins share with SP would likely be downweighted below the threshold used for reporting. And so SP would no longer appear on my cousin's roster of DNA matches, and likewise my cousins would no longer appear amongst SP's DNA match. Additionally, one would expect that many small, sub 10 to 15 centimorgan matches would similarly be depreciated beyond the reporting threshold. So the cumulative effect of endogamic tailoring would be for test takers of all backgrounds to have fewer total DNA matches, with some matches shifted towards lower centimorgan values, but overall we'd have more accurate matches reflecting genuine ancestral connections. Endogamic tailoring is listed among the steps of this flowchart, second from right. If we were to break down the endogamic tailoring process into constituent operations, the process looks something like this flowchart. What you're looking at here is the sort of process flowchart a programmer would use to add endogamic tailoring to the reporting structure of a DNA testing provider. You'll notice that step 3 in the top row of the processes here employs the shared match differentiation tool to determine whether our shared match trio is a favorable trio, in which case we ignore it and move on to our next trio, or whether our trio is an unfavorable trio and is a candidate for triangulation. I have a flowchart of the SMD process taken from my previous GFO presentation. It looks like this. Of course, this is the level of step-by-step granularity that would only be of interest to programmers or possibly someone working on building their own bioinformatic tools, but it can be interesting to see what precisely goes on under the hood from time to time like this. Now, it might go without saying, but don't attempt endogamic tailoring at home. And what I mean by that is that even though I've created a shared match differentiation tool, which you can use in Excel to perform the SMD process, which is a big part of endogamic tailoring, in order to perform the process properly, you'd need to download the entirety of your own DNA matches, which is doable, and then the full set of DNA matches for each of your matches, which would entail tens of thousands of sets of DNA matches. And then, in order to perform triangulation on each of those shared match trios, you'd also need the raw DNA data for each of those shared matches, or your shared matches would all have to upload their raw data to GEDmatch, which isn't a realistic possibility. For this reason, unlike my previous bioinformatic processes, there's no desktop prototype for endogamic tailoring. It really needs to be integrated into the back-end reporting server of a DNA testing provider, and of course, the larger their data set, the better. So in summary, we can recap the effects of endogamic tailoring. Where endogamy is concerned, there are some things we can't change. We're still going to have a restricted gene pool. People will be related to each other along multiple ancestral pathways, although it's worth noting that the effects of ancillary distant connections will be reduced. Pedigree collapse is what it is. As I discussed previously, if you can point to something on your family tree which reflects pedigree collapse, then that's not going to significantly change, and that's as it should be. However, other things will change. Many of your matches will share less DNA than before, but they will more accurately reflect genealogical norms for their underlying relationship. DNA matches with no discernible common ancestor will be reduced or eliminated from your results. Spurious matches will be reduced or eliminated, which in plain English means you'll see fewer small and false matches. Now, prior to my previous presentation, I created a genealogical bioinformatics Facebook group. At the moment, there are around 40 members of the group, and at the time I created the group, I'd hoped that it might foster an exchange of ideas, if only to curate suggestions as to where genealogical bioinformatics might be applied to address problems in the field of genetic genealogy, in the manner in which we've taken on endogamy with endogamic tailoring. And I'm still hopeful that the group may take on that role as more people become familiar with this field of inquiry. So if you're the least bit inclined, please visit the group at the link I provided. I look forward to seeing all of you online. Also, I've recently been awarded a genealogy research grant from the American Society of Genealogists, which will fund the preparation of instructions instructional materials on genealogical bioinformatics, and I expect to field test drafts of those materials in the group as they become available. Now, to return to our friend in the ill-fitting suit, this time courtesy of Gemini's Nano Banana AI, endogamic tailing, start with this and with the suit on the right. Finally, don't forget to visit my website at discoveringnewancestors.com for downloadable resources and utilities, in addition to case studies and other interesting bits of digital ephemera. Thank you all.